All right, welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. We're doing Linear Algebra 1. This is Chapter 2, Matrices. Section 2.4 is going to be determinants and their properties. This lecture, specifically what we're going to do is the definition of the determinant of a square n by n matrix and some examples. This is technically the definition. We're just going to show you this to motivate the next two videos in this section, because we're going to get, in the next two sections, we're going to get cofactor expansion and then determinant properties for efficiently computing, not using the definition. You're like, why would you make me learn all these other two sections? Otherwise, you have to understand the actual definition, and that's horrible. And I don't even want to explain what the permutation group is, or what the sign of a permutation is, and what a transposition of a permutation is, and what the heck are you talking about? Yeah. This scary beast. Luckily, for a real number, the determinant of a number is just a number, so that's good. But we're going to go from a 1 by 1 to a 2 by 2 to a 3 by 3 to an n by n. Oh my goodness. And so let's do that today, and then we'll get a formula for efficiently computing this, not using the horrible definition. Let's do it. All right, I caught one. Oh, haha, caught both of them. Here's Ringo and Alice. These are the monsters that you'll hear running around in the background. I'll try to get the reduction out of there. Critters running around. That's what's attacking my feet as I try and do this, right? Stop. Ow. That's my foot. I need that back so I can go do the video. We'll just put a video of you trying to use markers. We're going to get fake ones where we pretend like they're doing the computer work for us and stuff. Okay. All right. Definition of a determinant is going to be defined recursively. What that means is we're going to define the n by n determinant through the preceding or smaller size determinants, starting with the 1 by 1 and 2 by 2 determinant. Therefore, we'll start out with baby steps. The first determinant you're going to like, the second one you'll be like, oh, that's actually not so bad, and then the third one is going to be horrible, and then from there it's going to be terrible. And first going to give us ourselves notation for this horrible beast, and then this is sort of catfishing at first. It's going to be awfully nice at first, and then it's going to become an extremely larger and larger computational nightmare as we get to 3 by 3 and then a 4 by 4 and then an n by n determinant. So what is this? If A is a real number, and this is overkill, so obviously we're just going to write it as a number, but technically what we mean is that's a matrix which consists of one row and one column of entries, or one entry, which we call a real number usually. If I have a real number, the determinant of a 1 by 1 matrix, or the determinant of a real number, is equal to the only entry in that array, which is, in our notation, we're going to write the determinant of a number is itself, long story short. And in particular, what we're going to do is we're going to have a bunch of notation. Our notation for determinant, among other notations that I'm going to use, are we're going to write det A, or we might write det Aij to denote the elements inside there if we need to. Sometimes we use vertical lines, which, caution, shouldn't be confused with absolute value, which in videos later you'll see we're going to have to actually take the absolute value of a determinant, and then we get something that will look like that, and that's something else in our thing called a norm. In one of our other chapters we're going to talk about as well. So we're going to have some notation problems, but there's powers that be, and classically this is the notation we use. And in particular, this absolute value type notation does become extremely useful when we actually have to compute, because this is what it's actually going to look like when you're given a matrix. We're going to have to compute the determinant, which is now, here's the subtle difference. If I have ticks in there, that's an n by n matrix, which is in dimension Rn squared. If I take those off, we're going to algebraically compute a number from a matrix, which is a function from Rn squared to R, which is going to create a number. This is going to be a real number. This is what everyone else doesn't see. So if there's little ticks there, matrix, no ticks, determinant, which is a number from that matrix, which is just a real number. In particular, for a 1 by 1 matrix, the real number that you compute is itself, so you don't have to do anything. And then we're already going to get conditions on when this determinant is non-zero will tell us if we're invertible or not. That will also be one of the ideas of determinant. It's going to determine when a matrix is invertible. Let's do the 2 by 2 case, and then it's going to get worse from there. Okay, for a 2 by 2 matrix, I'm going to use indices, and then in the next scene quickly what I'll do is also I'll write it as A, B, C, D. But if you have a determinant A, B, C, D, it's going to be AD minus BC. We're also going to get some color coding. The determinant of a 2 by 2 matrix is a real number. Remember, every time this is a real number that we're computing. And that real number comes from here, and there's a formula for a 2 by 2s. There's a nice arrow type formula that you can give yourself to remember this. If I do this one, that is, you multiply those two guys together and I get those ones. So the main diagonal, if you multiply those, you get a positive term. So the main diagonal product is the first term, A11 times A22. And then the off diagonal of the 2 by 2 matrix or determinant, these guys' entries are, you get a negative term, so you subtract the off diagonals. And that's how I memorize the 2 by 2 determinant, AD minus BC. When we have A, B, C, D, or A1, the diagonal entries minus the off diagonal entries. This will become extremely useful because actually technically what we've already done is a 2 by 2 determinant is defined recursively as 4 1 by 1 determinants, which we just call real numbers. But technically they all have little brackets around them and they're 1 by 1 matrices. The next thing we want to point out is we define the 3 by 3 recursively based on 2 by 2s. And then we're going to define 4 by 4s based on 3 by 3s and 5 by 5s on, it's a Matryoshka doll, and it's going to be nested, and we're going to open them up until we get to the 2 by 2s. And once we can open up and see all the 2 by 2 matrices inside that Matryoshka doll of determinant, we are going to compute all the 2 by 2 determinants, and those will give us a bunch of numbers, and then we put that up and clean it all up, and we get the single number, which is a real number, which we're going to call the determinant of an n by n matrix. You're not going to like the definition of this at all. This will be the single fundamental motivation for why we're going to do the next two sections will be the definition itself. Hard pass. You don't want to use the algebraic formula of determinant of an n by n matrix to compute it. We're going to get clever methods called cofactor expansion and determinant properties. For an example of this, let A be the first 4 prime numbers and let B be something arbitrary. I cooked it up by what are the divisors of 12, the proper divisors, other than 1. What are the determinant of these? 2 by 2 you're also going to like. You're like, 1 by 1 was itself, and 2 by 2 is just this, and it's not so bad. What is the determinant of A? This is, we write it, so see, ticks, matrix, no ticks, determinant. Now that's a number I'm computing, and that is always AD, 2 times 7 minus BC, 3 times 5, which is 14 minus 15, which is negative 1. The determinant of B is equal to no ticks now, 2, 3, 4, 6. Whenever one row or column of a matrix is a multiple of another row, the determinant is always 0. That will be one of our properties later, but this is going to be AD minus BC, 2 times 6 minus 3 times 4, which is 12 minus 12, which is 0. This matrix, what that's going to tell us eventually is this matrix has an inverse because it's not 0. And this matrix, even though all of its entries are non-zero, this matrix has no multiplicative inverse because its determinant is 0. Now let's look at and investigate a little bit into what's going on with these indices and how we define this so that we can define the 3 by 3 determinant from the 2 by 2 determinant. Okay, for a 2 by 2 determinant, to give us insight before we do the next 3 by 3 determinant, let's give us the algebraic thing that Cauchy actually sees and gives this definition of the algebraic formula for all n by n matrices. It's Mario versus Luigi basically. So why do we like a Luigi better? Luigi could do it. Luigi not afraid. Why is he not afraid? Well, in the indices it actually gives me more information than just calling them A, B, C, D. For simplicity, that gives me my brain, I can just call them A, B, C, D, and then if the notation is nicer a little bit. But when I want to see insight into how things are working, the indices are telling me things, the row and the columns I'm in. In particular, what we're going to do is just quickly give you a breakdown on the 2 by 2 scenario, and then I'll try it for the 3 by 3, and then the 4 by 4 I'm not even going to do. I'm just going to give you the horrible general definition of a determinant to scare you, and then that'll motivate you to watch the next video and how we're going to use cofactors and determinant properties to actually compute these things, not with the definition. So this is trying to scare you specifically and motivate you not to use the definition for a determinant except for the 2 by 2. Anything larger, we're never going to use the definition. The 2 by 2 are the only ones because it's AD minus BC. What we're going to do is First of all, I'm going to define a bunch of things. I don't expect you know how to do them. There will be a quiz right after this in 10 minutes immediately, and you better get it all right. You don't have to worry. The permutation group Sn, or in this case S2, is all the permutations on the set of objects X, which in this case we're just going to call two things. If I had a set of two things, 1 and 2, S2 is all the possible rearrangements of 1 and 2. Specifically, so you don't have to worry about that, this is the notation, one of the more cumbersome notations, but it shows you what's going on. Here's the permutation sigma, which is the identity permutation, which we usually call E, but I won't spare you. You're like E sigma, it doesn't matter, I'm confused either way. This one we're going to call tau. What that says is this permutation takes 1 and it moves 1 to 1, it leaves 1 alone. And it takes 2 and it moves it to itself. So this is the identity, it doesn't move or rearrange 1 and 2. The other way we can rearrange two things is we can move 1 to 2 and 2 to 1. So we can rearrange these things. And this is what Cauchy starts noticing, especially for 3x3 and 4x4. He wants it to give us an algebraic formula. In the 9 chapters of mathematical art, they have 2x2 and 3x3 determinants, but they couldn't find a formula for the 4x4. It took several thousand years before, it took at least 1,500 years before Cauchy comes along and gives a systematic generalization to the determinant for all of them. And this is what we're trying to show you and scare you at the same time before not using the definition. Once I have these objects, what Cauchy sees is I need a little bit more terminology and notation. These things are called permutations. They're things that permute or rearrange a set of objects. So we call them permutations. They're actually functions, don't worry about it. Signum or sinum, or the sign, not sine or sine. The other ones, it's not a sign that we have. Technically it is. And it's not sine like the sinusoidal guy, bosom of address. It's not that guy either. It's another one, which is going to be the notation SGN or sinum of this permutation. It's either 1 or minus 1. Cauchy will give us a much better way also of using cofactor expansion. The cofactors will deal with this negative. But for now, every permutation, and I'm not going to get into it, these permutations can be rewritten as what we call transpositions, which are 2 cycles. What's a cycle? A cycle is something, blah, blah, blah. We're going to get a bunch of these 2 cycles. Every permutation, this will be a whole nother video on permutations and their cycles. But it turns out fact, every permutation can be written as a product of an even number of 2 cycles, transpositions, or an odd number of transpositions. So anytime you take Sn, if you take an arbitrary permutation in there, rearranges them in some way, it can be written as a nice group of an even number of 1, 2, and 2, 1, 2 cycles, or it can be written as an odd number of 2 cycles. It's harder when you only have 2 things. When you have more than one thing, you can have 1, 2, 3. It can be written as 1 goes to 3 and then 3 goes to 2, cleverly. So he's an even permutation in S3. Not going to get into it. For you guys, either you have that the sign of a permutation is either a 1 if the permutation is even. I'm not going to make you tell when they're even or odd. And it's -1 if you get an odd permutation. I'm just going to use this horrible notation of what Cauchy sees to give a generalized definition for an n by n determinant. Let's see that this actual horrible definition works for a 2x2. We know the definition of a determinant is, for a 2x2, is A11, A22 minus A12, A21. Now, I rewrite this as a 1, which is the sign of this permutation, because he's the identity. The identity can always be written as an even number of permutations. But this one can be just written as 1, 2. This one can be written as 1, 1 and 2, 2. These 2 cycles, technically that's our lazy way of saying 1 goes to 1 and 2 goes to 2. This one can just be 1 goes to 2 and 2 goes to 1. And that's why they call it a cycle, because it cycles around. So this one's an even permutation, so I get a +1. This one's an odd permutation, so I get a -1 in that term. And then if you look, this is permuting the indices. What we've done is we've permuted the permutation on the indices. So we have 1 and then sigma of 1, which is itself because it didn't go anywhere. And then we have 2 and then sigma of 2 because it didn't go anywhere. So that's actually what we're writing, is the permutation of the indices, the product of the permutation of the indices. And then in this one, same thing, but now we have a permutation that moved things. We have 1 moved to 2 and 2 moved to 1. So then how we're writing that is, with this one, we're writing that as 1 and tau of 1, because tau moves it to 2. And then 2 moves to 1, because that's tau of 2. Don't worry about too much. But what I'm lining up is, you can see that what we're going to write this now as in general is, a determinant of a 2x2 matrix is the sum of all the permutations in S2 of the product of the permutation of the indices. of those entries. Something like that. You don't need to know. The whole point is I'm trying to scare you with this definition. Let's do the 3 by 3 and then the general n by n, and then we'll motivate for the next video for cofactor expansion and not using this definition. All right, definition of a 3 by 3 determinant is going to be, here's a 3 by 3 matrix. What is the determinant? It's this hot mess. This is technically the definition of a 3 by 3 determinant. So it's going to be, notice first of all, I've got 1, 2, 3, 4, 5, 6 terms. 3 of them are positive and 3 of them are negative. And then if I think about this for a second, if I look at x, which is 1, 2, 3, oh, that was not 3, huh? I don't know who that was. Then the permutation group S3 has 3 factorial, which is 6 permutations in it. First of all, let's see how just algebraically cleverly, and this has been in the 9 chapters of mathematical art, they still teach this in China in school. When you're going to compute a 3 by 3 determinant, you want to use the Chinese method of cleverly writing it down like this. First of all, I need some, no, that's a sextant. No, that's an electrical wire. Oh, there's one of them. Okay, I need some markers. I got wizards have stuff in their pockets. I need a couple markers to do our color coding again. What we're going to do is, I'm going to do just like the 2 by 2 determinant. I'm going to draw some arrows for a second, and then hopefully I can enlighten what's going on here. So first of all, we have 3 down arrows. Again, yeah, making sure they're kind of, he's in there. Line of best fit. This is least squares. We're going to talk about that in later videos. And then we're going to get 1, 2, 3. Now notice that we have the red terms are going to be the positive terms. Positive, positive, positive. And then the ones that green arrows are going to be the negative terms. So therefore, technically, if you want, what you do is you write down your 3 by 3 matrix. You write down column 1 and column 2 again. And then to compute a 3 by 3 determinant, you can multiply all these 3 numbers together, and then add it to these 3 numbers multiplied together, then add it to these 3 numbers multiplied together, then subtract it from these 3 multiplied together, and these 3 multiplied together, and these 3 multiplied together. Remember, these could be numbers like multiply 2020 times 2019 times 2018. I don't want to do that anymore. That's just one of them, and then I'm going to have to do that in all the terms, and it depends on what you've got, and we give you small, usually integer numbers at first to compute, but the universe doesn't really care how big the numbers are. This is going to be extremely large. I'm not showing you, but for a 10 by 10 determinant, by definition, it would take over 10 million addition and multiplication operations to compute it by definition. Yeah, it is not going to be feasible at all either. And then I'm going to continue talking about the 3 by 3 scenario and then give you the general n by n definition in a second. But this is the motivation for we never want to actually use this definition to compute. The internet uses matrices which have to compute determinants for these matrices, and they're currently about 5 billion by 5 billion square. 5 billion rows and 5 billion columns. I am not using the definition to compute the determinant of this thing, but they can compute the determinant of it. So how are they doing this? With supercomputers and a different method, which we're going to do in the next video. All right, from here, what I also want to notice is, should we do it live or we might have to edit, but let's write down the 6 permutations in S3. The first one's easy. 1 goes to 1, 2 goes to 2, and 3 goes to 3. Then I know that there's going to be 3 that have a fixed number. 2 went to 2, 1 went to 1, and 3 went to 3, but then the other interchanged. So I have done this before, so what I do is 1 went to 1, but then 2 went to 3, and 3 went to 2. And then 2 stayed fixed, and 1 went to 3, and 3 went to 1. And then 3 was fixed, and 1 went to 2, and 2 went to 1. And then we're going to have 1, 2, 3, 1, 2, 3. Then what are the last ones? 1 went to 2, 3 went to 2 went to 3, and 3 went to 1. Or then we can have 1 went to 3, 2 went to 1, and 3 went to 2, I believe. Yeah, 3, 1, 2. 2, 1, 3, and 3, 1, 2. Either way, there. We have the 6 permutations. This is what we call S3. And there's 3 factorial, which is 6, my point. Now you can match each one of these, which I should have done with the indices anyways when I was doing that. You can match 1 went to 1, 2 went to 2, and 3 went to 3. And because he was plus, that turns out in this one, the identity is always an even permutation. Next, I had in this one, 1 went to 2, 2 went to 3, and 3 went to 1. 1 went to 2, 2 went to 3, and 3 went to 1. So that is this permutation right here. We can put them in color again now. Red, red. And then this one, 1 went to 3, 3 went to 2, and 2 went to 1. This one is this guy. And then, of course, these 3 are going to be the green ones. That means that these are even permutations in S3, and these are odd permutations in S3. And then we got minuses for those ones and pluses for those terms. What that tells us is, given our horrible sum definition, determinant of a 3 by 3 matrix is equal to the sum of all the permutations in the permutation group S3 of the sign of those permutations, either a 1 or a -1, times the product of the permutation of all of the indices. And then we have A2 sigma 2 and then A3 sigma 3. This is the sum over all the permutations of the sign of these. And then what is this going to have? Or we can write this from, there's 6 terms. 3 factorial. This is, I hope, scaring you into not wanting to ever use this definition. So we're going to get cofactor expansion in the next video, and then we're not done. After you get cofactor, like, I like that, but yeah, it's not the most efficient to do 4.5 billion or 5 billion matrices. We need cofactor expansion in combination with determinant rules, and then we can efficiently compute determinants. Let's do an example of this. Einstein's biggest mistake is the cosmological constant. Sometimes mistakes are all right. Find the determinant of this 3 by 3 matrix, and we haven't given you any machinery. This is what we're trying to motivate again. If I don't give you cofactor expansion or determinant properties, yeah, you're stuck with the definition of, oh, A11 times A22 times A, yeah. Because that's all we have, I'm going to use the 9 chapters of mathematical art method. I'm going to write down the first 2 columns again, and then I'm going to do 1, 2, 3, 1, 2, 3. And that is not going to be fun at all. I'm not planning on enjoying myself. Well, it's a little bit fun because I'm doing math computations, but you're going to not enjoy yourself very much. And the motivation here is we're not going to use this method in general. We want to find a faster way that will compute the same number, but will speed up the process significantly. Orders of magnitude in polynomial time when you actually have to start computing huge ones. Less talk, more action. I'm going to write down now ticky-tickies mean that it is a matrix 3 by 3. Once I take the vertical bars, I'm computing a determinant, a number from them, from the matrix. Therefore, I have 1, 2, 0, 3, 4, 1, 4, 1, 5. The 9 chapters of mathematical art say write down these 2 columns again. -1, 2, 0, 3, 4, 1. And then we're going to use our color code. We're going to do 1, 2, 3. And then we're going to do 1, 2, 3. And then now, I don't need those. What we're going to do is the 3 red ones. Now you can see, we'll do it in stages. This is going to be -1 times 4 times 5. The negative came from the fact that the entry was negative, not because these are positive terms. There's going to be negatives everywhere. Plus, that was the first term. A11, A22, A33. Now the next term is plus because it's a red arrow. 3 times 1 times 0, which is going to be gone. Plus, this one is positive. 4 times 2 times 1. Then we're going to get minuses of the green ones. Minus a 0 times 4 times, I don't care. Minus 1 times 1 times -1. And then here, I'm going to get minus 5 times 2 times 3. Which is going to give me gone, gone. This is now equal to -20, be careful, plus 8, plus 1, minus 30, which is -50, plus 9, which is -41. Ooh, that's what I got when I did this ahead of time to make sure it would be right, so good. I didn't, I'm a wizard. There, -41. That was a whole bunch of, now you just saw And these were integers that I gave myself a 0 so that I knew it would kill a couple of the terms. If you have all non-zero numbers and then they give you 2-digit or 3-digit numbers, I am not going to want to compute those 6 groups of 3 multiplications at a time and then add and subtract them all together. And then if they're all positives or negatives in the right spots, these could all turn into positives and you have to add and you get a huge number. We want a faster way of computing the exact same number. The number is going to be unique. The determinant has to be -41, however we compute this, because it's actually a function, so it's only got one value. -41 has to be the number we can create from this matrix via the determinant. What we want is a much faster method of doing that. Let's look at, now that we have, you can see, technically you can compute 3x3 determinants. You're like, I'm good enough. And same as in the I-Chien, 9 chapters of mathematical art. I can compute 2x2s and 3x3 is good enough. What if I, for some reason, need a 4x4? How do we compute that and what is the definition? Can you build with that? Yeah, so we don't want to do that at all. What we're going to do instead is follow Cauchy and get algebraic formula. Cauchy and Lagrange, I can't remember. I'll have to look it up and make a note of who actually did prove this first, but we're going to get cofactor expansion along the top row and then any row or column, and that's going to give us a much quicker computational way of computing the determinant. That's still not fast enough for us, and you have to think of billions or huge matrices, and then what we're going to want in the next section is also determinant properties, and that will extremely speed that up. I'd like to think you'll learn a few things hanging out with me. I'd like to think this. Let's re-look at a 3x3 determinant. What Cauchy's trying to see, I think. The determinant of a 3x3 is, here's the clever formula, I have 3 positive terms, I have 3 negative terms. What I also start noticing is I have 2 terms that have A11 in them. I also have 2 terms that have A12 in them. And then the last 2 I don't have to corner off, they have. So this has, I noticed they both have this guy in them, and this one both have A13 in them. What Cauchy sees and what we claim is that this definition is recursive. So we're trying to see that this 3x3 determinant can be computed by doing some combination of 2x2 determinants and 1x1 determinants, which is, these are already 1x1 determinants. What Cauchy sees, and hopefully you can see this is a 2x2 determinant, this is a 2x2 determinant, and this is a 2x2 determinant. Can you see it? Pause and try to see it from this matrix. Can you see that? If you can't, now I'll show you. This is equal to A11 times a 2x2 determinant, AD minus BC. And who is that? It's this determinant he notices, this 2x2 determinant. So this is A22, A23, A32, A33 minus A12 times this guy. Who is that? Well, if you block off this column and this row, it turns out it's this 2x2 determinant. A21, A23, A31, A33. This minus this, a 2x2 determinant, plus now A13 times this determinant. Hopefully you see where I'm going with this now. If I block that off, this guy is going to go right there. Oh, you drew on the picture. It's mine. I do what I want. This is A21, A22, A31, A32. 2x2 determinants, 1x1 determinants. It gets a little bit better. Now what we see is this will be the complete cofactor expansion of a 3x3 determinant, we're going to call it. This is now A11 times -1 to the 1 plus 1. A22, A23, A32, A33 plus A12 times -1 to the 1 plus 2. Odd, so we're going to get a negative times this 2x2 determinant. A31, A33 plus A13. Hopefully you see where I'm going with this. -1 to the 1 plus 3 is 4, so it goes away, but that's the formula we're getting at. And then I have A21, A22, A31, A32. What we're doing with that is this thing we're going to call a minor, this thing we're going to call a minor, this thing we're going to call a minor. A different kind of minor. It's not the minor that digs a coal in the mine. It's not that guy, and it's not the 17-year-old not allowed into the bar. Those are different minors. This is our mathematical minor, which is going to be obtained from a matrix by blocking this M, who is this guy now? M13, the minor. M13 is obtained by blocking off row 1 and column 3 of that original matrix to get a sub 2 by 2 determinant, and that's what we call a minor. And then this -1 business guy times these minors is what we call a cofactor. And therefore we write this as A11 C11 plus A12 C12 plus A13 C13. This is the determinant of a 3 by 3 matrix. This is what we're going to do in the next video, is we're going to define what a minor is, we're going to define what a cofactor is, and then I want a minor to be a minor, a 17-year-old who works at a coal mine. I know some of those, a minor that knows about minors. We're going to do a video. The next video, we're going to do minors that are minors that know about minors and cofactors. Please subscribe right here, hit the notification bell. We'll talk about minors.